Hello everyone, I'm J Wildberger. So in this lecture we're going to move our course on linear algebra online, and we're going to be looking at complex numbers and in particular the exponential today. So even though there's some challenges in moving in this direction, we can meet those challenges and we can still learn a lot of interesting mathematics. And in some ways there will be added opportunities to explain things to you visually and using some additional tools that are maybe a little bit more accessible in the online space. Okay, so a good place to start is just by having a quick review of the basic things that we already know about complex numbers to set up this exponential function that we will then be interested in connecting that with more familiar cosine and sine, the circular functions, and we'll be able to actually extract some interesting new information about those from this complex point of view. Okay, so let's start here with just the basics of complex numbers. We'll start with the complex number z, let's say a plus bi. Then I remind you that the complex conjugate z bar is a minus bi. And the a is called the real part of z. And one way of getting that is to just take z plus z bar over 2. Take the average of these two, and you're going to get a. And if you want to get b instead, that's the imaginary part of z, then you take the difference of z and z bar. But now you have to divide by 2i. Because when you take z minus z bar, you get 2 times b times I. Okay, so these are important little formulas that allow us to extract the real and imaginary parts of a complex number just from the complex number and its conjugate. Okay, so in terms of visualization, we're in the two-dimensional plane. We might put 1 here and I here to orient us. So this is the usual x and the y-axis. We have our complex numbers, a z equals a plus bi up here. X-coordinate is a, and the y-coordinate is b or bi. Now, in addition to this, there is also polar form for this same complex number. That involves, first of all, the modulus of the complex number, r, and also the angle or argument of the complex number, theta. So let me remind you how those things are. So r is the length of z, okay, and that's the square root of what I like to call the quadrants of z. In other words, the quadrants is just z times z bar. So that's another way of thinking what r is, the square root of z times z bar. And if z is a plus bi, that's just the square root of a squared plus b squared. Now what about the angle? Well, the angle theta is determined from this right triangle here that we have. This right triangle here, and with sides b and a. So we could write theta equals tan inverse of b over a, or if you prefer, arctan of b over a. Now there's a little bit of complexity involved in the angle. So an angle is only really defined up to a multiple of 2 pi. So theta is defined up to 2 pi. So there's a bit of ambiguity when specifying the angle. Generally speaking, we're thinking about an angle as being a directed angle in this context. So we're measuring from the positive x-axis, this one here, to the vector from the origin to z. Okay, and that's where we determine this angle. Now, if we want to remove the ambiguity involved in this angle, we have some alternate notation. So first of all, the notation for theta is that it's the argument of z. Okay, argument of z. Argument. And of course, the r up here is the modulus of z. So we have the modulus and the argument. Now, if we want a well-defined angle, we have to choose a certain range of values that we want our angle to be in. And we can do that by sometimes what's called the principal value of the argument. So capital A arg, okay, so it might be called principal value of arg. That is the angle. This is the angle theta, which is which is arg of z, where the angle is between minus pi and pi, strictly bigger than minus pi. I should make that a little bit clearer. So there's a minus sign there. So strictly bigger than minus pi and less than or equal to pi. Geometrically, what that amounts to is that we're agreeing that we're going to be measuring from the positive x-axis in this direction up to and including pi, so up to including pi, or we're going in this direction, in the sort of the negative direction, up to but not including minus pi. Okay, that's the range of values that we're considering. And since that's an interval of length 2 pi, any angle otherwise that we get can be by suitably adding multiples of 2 pi, get in that range there. Okay, so that's all, I hope, pretty familiar. And now let's have a look at what we were talking about last time. We were talking about how the unit circle and its multiplication is a very interesting object. So the unit circle, here it is, again, 1 and I. It's defined in Cartesian coordinates, of course, by x squared plus y squared equals 1. But in the complex world, it's described by the modulus of z squared equals 1, or just the modulus of z equals 1. And a typical point on this unit circle has the form z equals cos theta plus I sine theta, right, which just simply corresponds to considering an angle there, and then obviously the x and y coordinates of that point are cos theta and sine theta. Now, we saw last time that multiplication on the unit circle was quite pleasant, and there's a fundamental proposition here. I might repeat it just so we make sure we remember that if we have two angles, say theta 1, and we have a point on the unit circle, cos theta 1 plus I sine theta 1, and we multiply that by a similar point on the unit circle with an argument of theta 2, namely cos theta 2 plus I sine theta 2, then the result of that multiplication is another point of the same kind, where the new angle is the sum of the previous angles. Okay, sum of the previous angles. So that's a very important formula, and has, first of all, a nice consequence. That's usually called de Moivre's theorem. That tells us something about powers of such a point on the unit circle. And the theorem is that if we take, say, cos theta plus I sine theta, and we raise it to the nth power, then we get cos n theta plus I sine n theta. And this is for any for any integer, n. So both negative and positive values. So why is this, and what is it telling us? Well, it's telling us that if we have a complex number on the unit circle, I might make it a little bit bigger this time. Okay, there's 1, there's I. Let's say there is z, okay, and it's cos theta plus I sine theta. Then that means that angle there is theta. Then if we look at z squared, well, it's going to be just what you get when you take two of those angles, both equal to theta. And theta cubed, well, it's formed by taking another angle theta, so z cubed up here. And so correspondingly, we could keep on sort of marching around the unit circle at constant radial intervals and get increasing powers of z. If we want negative powers of z, we should start with z inverse, which is down here. So for a complex number on the unit circle, the inverse is just the complex conjugate, which is cos theta minus I sine theta. Or if you like, cos of minus theta plus I sine of minus theta. So this is consistent with this kind of formula here. If n is minus 1, then they're exactly the same. And then, well, for higher negative powers, we will just be going in the opposite direction. So here it now is sort of minus theta. That's supposed to be minus theta. And then here's another minus theta. And here's another minus theta, etc. So here's z to the minus 2. Here's z to the minus 3, and so on. So negative powers of z march in this direction. Positive powers of z march in this direction. So this is very important, and it's a very different kind of arithmetic from what we're used to with the real line, the real number line, because there's really this two-dimensional aspect of these powers. If we take powers of a number on the real line, like let's say here's 1.2, and we take powers of it, well, we know that we're just getting numbers that are increasingly spread out in this x direction. But here we're going kind of around the circle as we take power. So that's quite interesting. Now, as for the proof of de Moivre's theorem, well, that's in some sense almost obvious from this diagram. If you understand geometrically what we're talking about, we've just seen that you just add the arguments when you take powers. So when you combine that with our understanding of the inverses, then it's kind of obvious. But if you also would like a sort of more formal proof, there is a proof by induction, and that is in our notes, and I suggest you have a look at it if you like. Okay, so that's an important result. Okay, great. So now we want to connect all of this with the exponential function. But before I do that, I might actually shift gears just a little bit and show you a little bit about GeoGebra, okay, which is kind of fun. So GeoGebra is a dynamic geometry package that allows us to visualize geometrical things. And it also helps us visualizing algebraic, calculus kinds of things, and also, in fact, complex numbers. So here's the XY plane, and I'm just going to show you, if you're not familiar with it, sort of what you can do. So I'm going to input something here. In fact, I'm going to input the unit circles equation, x squared plus y squared equals 1, and I'll enter that. So now you see the circle here, and its equation is up here. I don't really like the name equation 1. Whoop, I deleted it. I shouldn't have done that. Control Z, I get it back. Okay. What I should have done is I should rename it. So let's rename it. There's its sort of information. Let me call it C for circle. Okay. So there is the unit circle. And we can actually work with this in complex plane. So one way of doing that is to take the point up here, and of the various options for point, there's a complex number tool. So if you click on that, and then I click somewhere, okay, then you can see over here I'm getting the point 3 plus I, and it's called Z1. There's a little index here that you can't see, but you can see it over here. So I might do that again. I might choose another point. How about this one here? Z2. That's 1 plus 2I. Okay, so those are complex numbers. So this thing can actually deal with things. So suppose I want to do Z1, I have to do perhaps plus Z sub 2. Let's see if that works. Oh, great. So you can see that the sum of these complex numbers is this one up here. And that is indeed how we add complex numbers. And if we wanted to multiply them, Z sub 1 times with a star in GeoGebra, times z sub 2. Let's see what we would get. Oh, it's 1 plus 7i. Where is that? I'm going to have to zoom out a little bit here. So there it is up there, okay? The product of 1 plus 2i and 3 plus I is up here. All right, so we could actually sort of illustrate some of the stuff we were talking about. If we make another complex number and then maybe try to stick it on the unit circle. Okay, so there's z sub 5. If I take z sub 5 and I square it, you see where it is? And if I take z sub 5 and I cube it, I get there. You can see that it is indeed marching across here like this. If I take z sub 5 and I raise it to the power minus 1, that's like inverting it, it's down there. And maybe I can even drag things. So if I take my arrow there and I drag this around, you can see what happens to the power. So I'm just moving the initial point, and the various powers are moving around. So this is quite a nice visualization tool that helps us understand what happens with complex numbers. Great. Okay, good. So let's go back to our discussion of complex numbers and want to introduce the exponential. So we've talked about this expression cos theta plus I sine theta representing a point on the unit circle right here. And we can maybe here introduce this new terminology. So cos theta plus I sine theta, we're going to say that that's also e to the I theta. Okay, so we're introducing the complex exponential. And that's a great tool because it actually does act like a complex exponential. In particular, if we have e to the I theta 1 times e to the I theta 2, well, that's just e to the I theta 1 plus theta 2. That's just a rewriting in this kind of language of the earlier result that was this one right here. This one right here. Yeah. And sort of in the same vein, the de Moivre's theorem becomes e to the I theta to the n, so taking the nth power of cosine theta plus I sine theta, I'll write it out, cos theta plus I sine theta. Well, de Moivre's theorem tells us that's cos n theta plus I sine n theta, so that's e to the I n theta. Okay, so that's those are two very important properties of the exponential function that mimic the way the usual exponential works. Okay, and it's in some sense a lot easier in many cases to work with the exponential rather than the cosines and the sines, and there's now an intimate connection between all three of these things. Okay, so before we go on a little bit more with that, I just have to tell you about polar coordinates for more general points, just to remind you about that. So if we go back to our typical point, z equals a plus bi, and here is our unit circle, let's say. And then we can think about sort of analyzing this in terms of modulus r, and also in terms of this angle theta. And this point here then will be cos theta plus I sine theta. That's the point on the unit circle in the direction of z, but of modulus 1. And then the point z will just be a multiple of this one. Okay, so we'll just get that z is equal to, in fact, r times cos theta plus I sine theta. And we could see that also just by observing that a is equal to r cos theta and b is equal to r sine theta. Okay. So this is a very general kind of expression for a complex number. That's a kind of a polar form. And now we see that we can also write a corresponding exponential polar form. All right. So exponential polar form, perhaps we could say, is that this same complex number z could be written as r times e to the I theta. That's a very nice way of describing a general complex number where r is the modulus of z and theta is the argument of z. And the advantage of this is that, well, multiplication is quite easy. If we have two complex numbers, both of that form, say r1 e to the I theta 1 and r sub 2 e to the I theta 2, well, their product is going to be what? The r1 and r2, we can kind of bring them together. And then the product of the exponentials is by this rule up here, okay? That rule there is just e to the I theta 1 plus theta 2. And this is then a very important relation that has a nice geometrical understanding. So we'll write it down as to multiply complex numbers. What we do is we multiply the moduli and add the arguments. Great. Okay, so the last thing I want to do in this video is to clarify the relationship between the exponential and the cosine and sine. So let's write that fundamental relation as e to the I theta equals cos theta plus I sine theta. And in the spirit of how we started the lecture, let's also look at the complex conjugate of e to the I theta, which is e to the minus I theta. So that's going to be cos theta minus I over here, I sine theta. Okay, and when we do the same kind of things to get the real and imaginary parts to this, we'll find that cos theta equals the sum of e to the I theta and e to the minus I theta all over 2. And the sine of theta, we have to take the difference of these. We have to take e to the I theta minus e to the minus I theta, and then we have to divide by 2I. Okay, so I remind you that's just the same kind of thing that we were doing up here. Okay, so right, so we have established these two relations now that express cos theta and sine theta in terms of exponentials. And this turns out to be a very powerful kind of thing. And it's so powerful that it's almost the case that any relation, any sort of circular or trigonometric relation that you have involving cosines and sines can be proven by making these substitutions and reducing everything to a formula involving exponentials. And exponentials are easy to do, easy to work with a little bit because of their nice multiplicative property. So we're going to have a good look at some examples of that kind of utility, exploiting these formulas to prove some nice trigonometric identities next time. So I'll see you then.